Good afternoon, everyone. I'm Chen Wang from the Department of Economics and Center for Global Business at Monash University. So before we start the seminar, let me first acknowledge the traditional owner of land. We acknowledge and pay respects to the elders and the traditional owners of the land on which our four Australian campuses stand. Okay. So welcome to the online seminar series on digital economy, jointly held with Hong Kong Baptist University, Renmin University of China, National Taiwan University, and Monash University. So today we are very happy to have Professor Julian Wright present in our seminar series. So Julian probably needs no introduction in the world of platform economics. So I'll make a very short introduction. So Julian is the Ling Chong Ya Professor of Economics in the Department of Economics at the National University of Singapore. His research focuses mainly on strategy and the policy questions related to digital multi-sided platforms. His work has appeared on top economics and business journals such as American Economic Review, Quarterly Journal of Economics, Review of Economic Studies, and Management Science. So there has been a lot of debate on whether online platforms or more generally firms can use consumer data as a barrier to entry. So today Julian is going to speak about this issue. Julian will have an hour to present. Then our colleague at Monash, Professor Zhijun Chen, will give a discussion of the paper. And then there will be 20 minutes at the end for general questions. So the audience can raise hands to ask questions directly during the talk, or they can send questions through the Q&A function. Julian can also pause a few times to take questions. So now, Julian, the floor is yours. You will have until 4 p.m., that is 1 p.m. in Singapore. All right.
Okay, thank you very much, Chengxi. Thanks for the introduction. Can you see my screen okay?
Yep.
Great. So this is joint work with Andre Hiju in Boston University. And as Chengxi mentioned, the issue about consumer data and sort of its role and competitive advantage is becoming quite a big issue in policy circles. I think in economics, if we think about data, the use of data, there's sort of burgeoning literatures on use of data for targeted advertising and privacy around that, and also for price discrimination. Arguably, there's a little bit less attention paid to the use of data to improve products, which, at least in my view, is probably going to be the biggest role of data in the years ahead. And this is what we're going to call data-enabled learning. Okay, so what we have in mind is that firms are increasingly learning from customer data to use that to improve their products. And there's a few reasons for this, of course. Largely, it's because a lot of products and services are becoming digitalized and are based in the cloud. Of course, data storage is much cheaper now. And probably most importantly, processing of data, by which I mean being able to get insights and predictions out of the data, has drastically improved with the use of new machine learning algorithms. So when you put all these things together, what it means is nowadays is increasingly customer data is becoming a key factor for firms in terms of improving consumers' willingness to pay for their products or services, and therefore in terms of their competitive advantage. And then in addition, we're seeing much faster learning. So in particular, we're seeing learning that happens while consumers are still consuming the product. So sort of real-time improvements as consumers use the product, which is of course a feature of this sort of digital cloud-based products and services. And thirdly, another consequence of this change is that a lot of the learnings now can be customized to individual consumers, rather than in the past where you might have had a product improvement based on some customer survey, and the next version of the product was improved, but that was the same for everyone. So there's, plenty of examples of this data-enabled learning in practice. Here I've listed a few. one thing to note about all these examples is there's a virtuous cycle going on. So if you take, say, Google Maps, which I think is familiar to most people, then as more people use this for their traffic predictions, then there's going to be better predictions because there's more, as people are using Google Maps, there's more data on drivers driving in any particular location. So you get better predictions, and as you get better predictions, more people will use it. And so you have this nice virtuous cycle, and that's true of all these different data-enabled learning examples. Another difference between these different examples would be some of them, there's a more use of data across different users. So if you think about, say, chatbots or autonomous vehicle systems or sort of security applications of data, then in these examples, the firms are learning from previous users' data to improve the product for other users. So sort of the learning is across users. In other examples, and I give an example here of a particular product, which is, fits under the smart connected devices, the learning is within the user, largely. So it comes from more and more customization to a particular user. So in this example, this is a bed that's sold in the US, which regulates the temperature, and it regulates the temperature to optimize your sleep. So it turns out temperature is a key factor in how well you sleep. And so by tracking your sleep throughout the night and the quality of that sleep, they can see how that correlates with the temperature, and then they can optimally adjust temperature automatically so that you get the best sleep. So in this case, a lot of the learning is learning about an individual user's sleep patterns and how they correlate with temperature, because everyone has a different sort of relationship to temperature. And so that would be an example of what we would call within user learning, where the learning is specific to individuals. And of course, in some of these examples, you can have both across user learning and within user learning. So recommendation systems would be a big class of examples where the firms are learning both, they're learning about each individual user from other users' preferences and also from that user's preferences. So obviously on Netflix or Spotify and so on, and I guess this is particularly the case for TikTok, where the recommendation system is a large part of the value that they provide. They're learning from correlations between different users and what they like and what a particular user likes, and then recommending things that other similar users also like. So that would be a case with both across and within user learning. So we're going to make some distinctions between these different types of learning. And so you'll see later how that plays a role, but just to sort of keep in mind, in the different examples, you could have just purely across user learning, which arguably Google Maps would be pretty close to that. Pure within user learning, like some smart connected device, like a thermostat device, or some combination of the two. Okay, so what are the questions we're asking? And then I'll pause to see if there's any clarifying questions on the examples or the motivation. We're asking basically, how does this data-enabled learning affect firms' competitive advantage? That's a sort of main question. And does that have implications for policies related to data? And we'll, in sort of answering these questions and thinking about the role of data, we'll distinguish between across user and within user learning, and whether they have different implications. And finally, under what conditions does this data-enabled learning create meaningful network effects? That is, network effects that where it actually changes the outcomes. Okay, so let me pause because I did notice there was something in the chat. I think that's just a general point. Okay, so any clarifying questions on the motivation at this point? If not, then let me move to the relationship with the previous literature. So there are two large literatures that this work relates to sort of fairly directly. One is the learning by doing literature. So learning by doing would be, firms as they produce more, they get better at producing, so their costs come down. And that's similar because here, as firms sell more, they get more data, and the willingness to pay of consumers goes up. So there's sort of a parallel. Instead of costs going down, here, willingness to pay goes up. It's similar, but only in the case when there's no learning within the consumption lifetime, because there's no parallel of that for the case with learning by doing. And also in the case where there's no within user learning. Again, there's no parallel to that in the literature learning by doing. So even in this case where we don't have either of these features, it's still different from what we do is different from learning by doing in a few ways. One is we have a completely different model. So we have a sort of model of vertically differentiated firms rather than horizontally differentiated. That turns out to be key in allowing us to get much more general results, our particular framework, the way we model the learning and the competition. And in particular, we get some very general efficiency in consumer surplus results and comparative statics on shape of learning function and so on, which that learning by doing literature we're not able to get. And then I think more importantly, we look at issues that were not issues in the learning by doing literature. So, even if we had used the same model and, there was this direct parallel because we weren't looking at learning within the consumption lifetime or within user learning, we're still looking at new issues, which were not issues previously, like data sharing policies and acquisition of data, privacy, this across versus within user learning distinction, and the role of beliefs and network effects. Okay, so that's, I think there's quite a lot that's new here compared to learning by doing. The second sort of big literature that this is related to is the switching cost literature. And this is in the case that we look at within user learning. So within user learning, it's going to be a bit like an endogenous switching cost, because the more the consumers buy from a firm, so they keep using the same firm's product, the more that firm learns about their preferences, and the more it customized for them, and therefore the higher the cost for them to switch to another competing firm's product. And so you could think of that as being a bit like a switching cost, which increases with the use of the seller's product. But as far as we know in the switching cost literature, no one's looked at that case where the switching cost actually increases the more you use the product. And so that would be a parallel. Okay, and then there's a more recent literature that's looked at, there are a bunch of new papers that look at models which I would classify under data-enabled learning, or they have some part of them looks at data-enabled learning. And I don't have time to go through the specific differences, but I'd say one main difference is ours is the only analysis so far that has a fully dynamic model in which agents are forward-looking and data learning accumulates. So that's, if you want a sort of high-level distinction between what we're doing and what they're doing, ours is sort of dynamic strategic model. Those have other sort of restrictive assumptions that don't allow for that. Okay, so any questions on the literature? Otherwise, we can get into the model. Okay, so here's the model. It's what I'm going to focus on, you can sort of see from the number of circles here, what I'm going to focus mostly on in this talk, given it's only an hour, is the model with across user learning, so pure across user learning. One reason for that is a lot of the modeling analysis results carry over with suitable modifications to the case within user learning, and also to some extent when we have network effects. So a lot of the stuff we need to do, we can do here, and then we can say how it changes. Okay, so in the model we have two firms, an incumbent and an entrant, I and E. You could think of the incumbent as being having more data, right? Like this incumbent entrant are going to be basically the same, other than a couple of differences. And one difference would be, that incumbent you could think of, why we call it the incumbent is because it starts with more data. Entrant might have no data or it has less data. Okay, they have the same marginal costs. They compete in prices, and it's over infinitely many periods. So profit utilities are discounted by delta in the standard way. In each period, we have a continuum, measure one, of identical consumers. So the identical consumers, meaning they view the two firms identically as well. And so this is, you should be thinking of Bertrand competition here, price competition, but in an infinitely repeated setting. And these consumers, they decide which firm to buy from in each period, and there's unit demands. Okay, and you can either think of a new set, measure one of consumers every period, or you can think of consumers that are long-lived, so maybe infinitely lived, but they can costlessly switch from period to period between the two firms. So there's no exogenous switching cost. And actually, we could have any combination of the two, right? We could have some consumers who are new each period and some that are long-lived. It doesn't really matter, as you'll see. And so then what is the utility that these consumers get from buying from the respective firms? So it's given by this specification. So there's two parts here. One is a standalone value. So standalone values could be different. So that's a bit like asymmetric Bertrand competition. You could have one with higher quality, one with a lower quality, so they have different standalone values. And then there's a part that comes from the learning. So there's a value that's offered by the firms that comes from the learning from data. So you should think of the NI here as the data, the past data that the firm has. And it's actually a measure of past customers served, or what's going to be equivalent in the model is number of past periods that that firm has won. And so this is the total measure of customers that it's served, and therefore the amount of data that it's accumulated. And the more data it accumulates, the higher the value it can offer. So that's the way in which learning happens. It's sort of all captured in this learning function. And this function Fi can be different across the two firms. So that's another source of potential asymmetry between the firms. They could have different learning functions. Of course, they could have different amounts of data. It's an increasing function, at least weakly increasing. And it has this property that at some point, firms have accumulated so much data that they've learned everything they can learn, and so you reach a threshold. So NI bar is the measure of customers required for firm I to reach the maximal learning threshold. So just in a picture, this would be an example learning function. It's weakly increasing, and at some point, at some threshold level, it no longer increases. Okay, and so the only properties we're assuming for the main part of the paper is that this is weakly increasing. We don't assume it has to be smooth. In fact, I'll show you an example later where it's not smooth, which we use for one application. It doesn't have to even be continuous, so it could jump up at some point. Just has to be weakly increasing. Okay, so firms have learning functions. They could be different, and they learn as they get more data, which comes from their past sales. Okay, so now we're going to think about how we, solve this model, work out the equilibrium. So let's think about the firm's value functions. So that is, what is the present discounted value of the firm's profit, incumbent's profit, and entrant's profit, given some state, and the state here is just the number of the total measure of past sales that the incumbent has had and the total measure of past sales that the entrant has, or in other words, the data that the incumbent has and the data that the entrant has. Okay, and we can think about the simple case that both firms are already at that threshold. When both firms are already at that threshold, then of course there's no further learning to be made, right? Both firms are offering the maximal value they can offer. They have the standalone value, and they have their learning from the full amount of data that they could learn from, and everything's stationary. And so this is a very easy case to solve, and we have an equilibrium here where, like a normal asymmetric Bertrand equilibrium, where basically the firm that offers the higher value, both combining their standalone value plus the value from learning, whichever firm offers a higher standalone value will win, and it will extract the difference between the two values. And it will extract that in every period because there's no change from one period to the next. And so the value of the firm will just be the present discounted value of that. Okay, so whichever one offers higher sort of current period value will win, and then it'll get the present discounted value of that difference between the two. So that means whichever firm, if we look at the difference in the standalone values, we can define this sort of cutoff that E wins if and only if it has a standalone value SE that's greater than SI by more than I's sort of value from learning is greater than E's value from learning. So everything's very easy to characterize in that case that we're at the threshold. And then what we can do is we can go back one period and think about, well, we'll go back one step and think about, well, suppose E is, it's not at that threshold yet. I is at the threshold, E is not. But if it was to win one more period of competition, then it would get to that threshold. So then we can ask, how much would E be willing to, what price would it set? Would it be willing to subsidize in order to win that period so that it can get to that threshold and offer higher value? So you could imagine the case that if E wins, then it actually offers higher value. And so it's going to get this value after it wins, if it wins one more period. And on the other hand, maybe currently it's losing when it's still not at that threshold. So currently its value is 0 because it's not offering enough to win. But if it was to win one more period, then it's going to get this positive value. And so it's willing, in that case, it'd be willing to subsidize the difference between its discounted future value, which would be this one, right? Where the inside part of this max, divided by 1 minus delta, if it wins versus nothing if it loses. And that's how much it would be willing to subsidize the discounted value of that in order to win this period. And then incumbent would have to compete with that. And incumbent would also be maybe willing to subsidize, because if it maybe currently it's winning, and if it loses, then E's going to catch up, and in that case, E's going to win, and incumbent's going to get nothing. So each firm may be willing to subsidize. The question is who's willing to subsidize more, and not just that, but when we take into account how much they're willing to subsidize and the current value that they offer consumers in terms of the standalone value and the value from learning, which one offers more? And that firm will be the one that wins in the current period. We can work out its value, we can work out the other firm's value, and then we can iterate this and sort of solve it recursively back, essentially using sort of two-dimensional backwards induction to work out the value functions in every period, or in any state, I should say, and starting from any point. And of course, not just the value functions, but the prices and the consumer surplus and so on. Okay, so that's maybe to sort of think about how we solve this, and the result is this equilibrium. Before I talk about the equilibrium, let me check if there are any questions about sort of model setup and analysis. No? Okay, so
there is a question in the Q&A session, so by Isaac Swift. So he said, if both firms are below their maximum learning threshold, would there be a Pareto improvement if the firms share some amount of their data with each other?
Okay, yeah, I see that. So let me hold off on that question, because we're going to talk about data sharing in a bit. So that's probably the best place to to answer that. So, okay, let me describe the equilibrium, and it has a nice characterization. So we find this, within Markov perfect equilibrium, there's a unique equilibrium which exists in which E wins all periods if and only if the difference in standalone values is greater than or equal to some cutoff, which we call delta, and otherwise I wins in all periods. Okay, so what is this delta cutoff that's going to determine the threshold for which firm wins? Well, if you look at this expression, it's, obviously it depends on the future values offered by each of the firms as they learn more and more. And if you just divide through by 1 minus delta, so divide this right-hand side through by 1 minus delta, what you can see is it's actually going to be the present discounted value of the value, present discounted value that I offers from learning or from data for all periods if it was to win in every period, because this would be increasing by 1 each period it wins. Another period it would keep going up until it reaches the threshold, and then it would be stuck at this level forever, less the present discounted value that E offers if E was to win in every period. So the cutoff is this difference, or it's proportional to this difference in the present discounted values of the surplus created from data along the two firms' respective winning paths. So that's this interpretation of this cutoff, and that defines exactly which firm wins in any period for any state. And you can think of this delta as capturing I's competitive advantage, which is, the thing we're interested in, right? Obviously, the higher is delta, the bigger the standalone value that E must have in order for E to win in any period. So delta is a measure of the competitive advantage that I enjoys, and we can study how that depends on different parameters and data, of course. Okay, let me interpret the equilibrium a bit more. So notice this, there is a virtuous cycle here, because once you start winning, well, you get more data, and that's obviously going to push up your delta, because this delta is increasing in your, so I's competitive advantage is increasing the amount of data it has, so delta is increasing in NI. So as it gets more data, this cutoff increases, so that makes it even harder for E to win. So of course, I wins again, and so on. So there is this virtuous cycle. And despite that virtuous cycle, there's no, in what I've described, there's no coordination problem for consumers. There's nothing like, like we get with a normal network effect where there's multiple equilibrium and consumers are trying to work out what other consumers are doing in order to, figure out what they should do. And the reason for that is twofold. One is, remember, there's no switching cost. So even in the case where consumers are infinitely lived, we assume there's no switching cost. So they can switch from period to period, whichever firm is offering more surplus. So they don't really need to think about future periods. The only reason why they need to think about future periods is if somehow their choices today would affect their options in the future. But because each individual in this model is infinitesimally small, basically atomless, then an individual consumer's decision doesn't affect, the learning that the firm gets. And therefore, if an individual switches from one firm to another now, that has no effect on their future choices. And therefore, there really is no coordination problem for consumers. They basically can just choose whichever firm offers higher surplus in the current period. So interesting property is that even if the consumers are myopic, we get exactly the same equilibrium. So that, of course, will change when we have within user learning, where the firms are actually, customizing to individuals' choices. But here, whether consumers are myopic or forward-looking makes no difference, provided, of course, prices can be used by the firms to subsidize consumers. Okay, I see there's a question in the chat, so that may be useful to clarify. which is the role of this threshold on NI, right? The upper bar on NI, which is, that there's no, at some point there's no future learning. And the sort of comment was that must help with the backwards induction solution, and this point about depreciation of data, and then considering steady state rather than some endpoint of learning. Yeah, so that would be a different approach. Let me just make a few comments about this assumption about, obviously we're using that as our way of solving the model. So one point is, there's no sort of restriction on how high that can be, right? So, at some point it seems reasonable you wouldn't reach this threshold. But yeah, if this appreciation, maybe, you never really get to reach it. So that's a good point. We can actually allow, in the paper we talk about, instead thinking about the limit case. So suppose there isn't that threshold, or at least taking that threshold to the limit. And we can do that under, very mild restriction on the learning function. So you could still think about what happens in the limit case. Another thing we do in the paper is we solve it for sort of a finite period game, and then take the limit as the number of periods goes to infinity. And that, again, when you take that limit, you get back to what we have. And when you do the finite period game, of course, it's easier to allow for when you have finite number of periods, there is sort of an endpoint, and you can solve backwards. So, there's different ways you could approach it. One advantage of the way we do it is we're able to get very general solution. We don't have to look for sort of, we don't have smoothness requirements and look for stationary points using derivatives and things like that. Okay, just a bit more on the interpretation. I think I already alluded to this. The competitive advantage that the incumbent has, obviously increasing the amount of data that it has, increasing in that threshold, increasing in anything that shifts up its learning function. And conversely, of course, decreasing in anything that moves the entrance, gives the entrant more data, increases the entrance threshold for learning or the entrance learning function. So I think that's very intuitive. Maybe something that's not quite so obvious in this equilibrium. It's not the case that the incumbent always wins, even if the incumbent's ahead. So even, this is very general, incumbent doesn't have to be ahead, but assuming the incumbent's ahead, it's not the case that the incumbent always wins. So how could the entrant win? Well, the entrant could win because even though it has less data, it may have a higher value, maybe able to extract more information from that data. It has a higher learning curve. So that's a sort of obvious case. But even if its current value from that data is less, so it has less data, it creates less value from that data, but it could still win. And why would that be? Well, it could win because its future value from that data may be greater. That is, it has more scope to learn. If it was to win and accumulate more data, maybe in the future its learning is, its learning curve is actually higher. So that would allow it to potentially subsidize more because it has more to gain from learning, and therefore by subsidizing more, it could actually win today. So that's very much a possibility in this framework, that a firm could win even though it's behind, just because it has a steeper learning curve, or the learning curve increases longer than the other firms. So it has more scope to add value from data. Okay, any questions on that equilibrium? So Isaac had another question. If both firms are below the, oh, sorry, that's the same one. So I think that's still showing up. Okay, we'll get to that data sharing in a minute. So let me talk about welfare first. So think about what is the welfare properties of this equilibrium. And it turns out that this equilibrium is actually socially optimal. Socially optimal in the sense that the right firm wins in every period. So despite the fact we have this virtuous cycle where it seems like one firm gets ahead, and once it's ahead, it has an advantage, and that advantage is increasing. Nevertheless, the equilibrium is such that the outcome is always efficient, in that the firm that wins, if it can only be one incumbent or entrant, that firm is the right firm, the one that maximizes welfare. We wouldn't change which firm wins in order to, we couldn't change which firm wins in order to increase welfare. So there's a sort of simple intuition for this, which is whichever firm creates higher present discounted value of utility along their respective winning path, that should be the firm that wins, right? If you think about from a welfare point of view. Since the costs are the same, starting from any point with any given amount of data, whichever firm can create higher value from winning every period, and given an equilibrium, one firm that wins is going to keep winning every period, that should be the firm that wins. And that's exactly what our cutoff measured, right? The cutoff measured whichever firm was offering higher present discounted value of surplus created along the winning path. Okay, so basically that firm can afford to offer a higher current utility plus subsidy, right? It's a very simple intuition. It turns out that if you look at the expressions in the paper and the logic behind it, it's actually much more subtle. But I think this is the best intuition we can give. It's subtle because actually the firms don't extract the utility they create. They only extract the difference between what they create and what the losing firm creates, and therefore they can't necessarily afford to offer. They can only afford to offer the difference as a subsidy. But that's true for both of the firms, and given the recursive nature of it, it turns out that we get back to this sort of intuitive property that whichever firm can create higher surplus, total surplus, along its winning path, that's the firm that should win. Another sense in which that's not obvious is we know that along that winning path, the losing firm may be subsidizing in an attempt to win, even though it doesn't win. And that's something I mentioned, when I was explaining the logic of how we solve the model. And of course, the winning firm may have to subsidize in order to compete with the losing firm that's subsidizing. And the fact that the losing firm may subsidize, that has some interesting implications for consumer surplus and data sharing. So if you think about the equilibrium, the nature of the equilibrium, and the asymmetric Bertrand nature of it, the consumer surplus that consumers get is basically whatever surplus the losing firm is offering, because the winning firm just has to match the surplus that the losing firm offers. The surplus that the losing firm offers would be the surplus of its standalone value, the value created from the product through data, and any subsidy that it's willing to offer, right? That it offers in order to try to win. So whatever that is, that's what the losing firm offers, that's what the winning firm has to match in order to win. And therefore, anything that decreases the surplus that the losing firm is willing to offer will decrease consumer surplus, right? And what happens as a winning firm gets ahead, the more it learns, the more it wins, the further behind the losing firm becomes, the less willing it is to subsidize, or the less it may subsidize, because it no longer has a chance to catch up. And therefore, the less it subsidizes, the less consumer surplus is offered to consumers. And what this means, the implication of this is that even though, from a welfare point of view, it's great, we get the socially optimal outcome, from a consumer surplus point of view, the outcome's not so good, because as the winning firm moves further and further ahead, that actually weakly decreases consumer surplus. because the losing firm can no longer afford to offer the subsidy, and so subsidy decreases and consumers are worse off. Okay, and that feature, which I think is an important feature that goes beyond the simple sort of Bertrand-like nature of the model, the fact that the losing firm is going to be sort of less competitive as it gets further and further behind, and therefore the amount that consumers are offered can go down as the winning firm moves ahead. That feature has implications for data sharing. Okay, so it would suggest that what we really need to do to help consumers is maybe help the losing firm catch up, right? Because helping the losing firm catch up increases competitive pressure on the incumbent. The losing firm offers a greater subsidy. The incumbent has to match that, so consumers are left with more surplus. So it's a bit like this coordination problem, in that if all the consumers could coordinate, they could be better off sometimes buying from the losing firm, because that would allow the losing firm to exercise greater constraint on the winning firm, and in the future they can be offered more surplus. And so that suggests maybe sharing the incumbent's data with the losing firm can help consumers by allowing the losing firm to catch up, and therefore increasing competitive pressure on the incumbent. So that's true, we see that in our model, but there's a second effect that one has to take into account that is also present in our model whenever this data sharing policy is anticipated. And that is that if entrant anticipates being able to catch up through data sharing rather than offering a subsidy, then its incentive to offer that subsidy is reduced. So there's a kind of free riding problem. The free riding problem, if you think about, think about firms having to invest to build up data, it would be very similar. It's say, well, if they know they can share incumbents' data, they're going to invest less. The entrant's going to invest less in building up its data. But perhaps that doesn't matter because it's going to share the data anyway. But in this context, investment here really means offering a subsidy to consumers. That's how they invest. That's how they get more data. They offer a subsidy to attract more consumers so that they can get their data, so that it can improve the product, so that they can get more data. So anything that reduces their incentive to do that is actually going to harm consumers, because it's going to actually potentially reduce their subsidy and reduce their competitive constraint on the incumbent. So there's two forces, one increasing the competitive pressure on the incumbent, one reducing the competitive pressure on the incumbent. And in our paper, even with this very general model without specifying the type of learning function, we're able to specify, sort of characterize when data sharing is good for consumers, when it's bad. And basically what we show in proposition 5 in the paper is that if the entrant's well behind, then data sharing is actually good, because anyway, the losing firm's not going to subsidize. So you have no sort of reduction in subsidy because it's not subsidizing anyway. But when E is sufficiently close to the incumbent, the entrant's losing, but sufficiently close, it is offering a subsidy. And when it's sufficiently close, data sharing policy will always reduce that subsidy and lower the present discounted value of consumer surplus. So data sharing policy can go both ways, and we characterize when it's good and when it's bad. So I think, in terms of Isaac's earlier question, if both firms are below their maximum learning threshold, would there be a Pareto improvement if firms share some amount of their data with each other? So I think, first of all, from a welfare point of view, whenever you can sort of share that data, obviously you're moving up the learning curve for both of the firms. So that's sort of can be welfare improving. So yes, in a sense that can be good, but not necessarily Pareto improving, because I think you could probably come up with situations where it was Pareto improving, but often I would think that's going to hurt one of the firms. and could even hurt consumers, as we've seen here, right? Depending on the exact specification. So hopefully that answers your question. Any other questions at this point to clarify? I think I have about 15 minutes more, so probably got to keep going anyway, and then we can obviously have time for Q&A later. So how about data acquisition? This one's new, it's not in the paper, but something we looked at more recently. And I think it's an interesting issue, which is suppose firms can acquire data from a third party. So this would be the case where, I mean, this is different from what they've been doing so far. So far, they've been competing for consumers to get data. And at most, they can win like measure one of consumers, so measure one of data each period. Now, suppose they can buy it from a third party, and that maybe involve more than measure one of data. Maybe you can buy many periods worth of data in one go. So first of all, they're not getting it from subsidizing consumers, and secondly, they're buying it maybe a bigger amount of data in one go. And suppose that firms bid, and the one that bids the most acquires the data. So there's some firms selling this data exclusively to one of the firms. Then we characterize the equilibrium outcome that would result, and we show that now we can no longer have social efficiency necessarily. So we can get social inefficiency, and the reason why we're no longer socially efficient is because it's no longer the case where we have that logic that the surplus offered to consumers, whichever can offer more surplus is going to win, because here the subsidy is not going to consumers. The amount that's paid for this data is going to a third party. And that's different from the consumer that gets, deciding which firm to buy from, which would, look at the subsidy and the value of the utility they get from the product. So there's a sort of misalignment between the two parties, and we can get inefficiency. And as an example, suppose I is already at the threshold, we can show that it always wins the data too often. So if I is at the threshold, E is not at the threshold, we can show that the incumbent will tend to win this bid for the data, so acquire the data too often. So always wins, we show it always wins when it would have been socially efficient for it to win, but it also wins for a range of standalone values which are greater than that cutoff, where it would be socially inefficient for it to win. And I think just to give a little bit of intuition for this result, which is, it's a little bit involved to prove, but basically you can think of the case where I is at that threshold, E is behind. By buying this data, it could catch up and get to that threshold. And suppose the standalone values are very close, right? Well, if E catches up and gets to that threshold and the standalone values are very close and the sort of learning curves are symmetric or close to symmetric, then it catches up, but it can't extract much value because basically the two firms are going to be equal. On the other hand, if I wins the data, well, it doesn't actually learn anything from the data because it's already at the threshold. But what it does do is it prevents E from catching up. And so it still gets this big difference, of being well ahead of the entrant. And so you can see that I might win because it's, it stands to lose a lot more from E catching up, even though maybe it was, efficient for E to catch up, because maybe E in that, after catching up, it's slightly better and offers slightly more surplus. One other thing we look at, which is not in the paper, but interesting for policy, is privacy. So you can think of data privacy as meaning that firms can now only use a fraction of their new customer data. So, they sell to consumers, they get new data for that period, but because, you have a data privacy policy, more consumers hide the data, so the firm cannot extract any learnings from that data. So if you model privacy in that way, you can think of privacy as shifting. It means that firms are only learning from a fraction of the new data, so the learning curve is sort of proportionally cut. So here's a sort of illustration. Imagine you have this sort of S-shaped learning curve. So no learning up to some threshold, then you have linear learning, then you hit the maximum threshold. And suppose I is here, so I has ni, is the amount of past data that I has. E is below, it has ne past data. And what happens after this sort of shift to a privacy, more aggressive privacy policy, which makes it easier for consumers to hide their data? Well, it's going to shift down the learning curve for both of the firms proportionally, so by some fraction. But of course, eventually, even though now it takes much longer, eventually they're going to get all the learning, they get to that threshold. So the question is, if we had this privacy policy, would it hurt the incumbent more or the entrant more? Obviously, it's sort of bad for both in a way, because it makes it harder for them to learn. But does it provide a competitive advantage to one or the other firms? So normally when we think about privacy policy, we're not really thinking about the implications it has for the competition between the platforms. But in our model, we can look at that implication. And suppose that the incumbent, as in this picture, suppose the incumbent is closer to the threshold than the entrant. And both firms are on the increasing part of a S-shaped learning curve. So we're exactly in this, as in this picture. Then if the learning technologies are the same, then the privacy policy, what we find is the privacy policy actually increases I's competitive advantage. And the reason for this is, if you look at this picture, E has a lot more scope for learning, right? It has more that it needs to learn to catch up, so it has more potential that it can learn. And slowing down that learning process for both of the firms therefore creates a bigger disadvantage for E, because it actually has this bigger scope for learning. You could see this if you imagine incumbent being very close to the threshold. Then a privacy policy would slow down the learning, but since it's almost at the threshold, that has almost no effect. Whereas the entrant being way back here, that will have a big effect. And we get an even stronger result if E's learning technology is better. Again, for a similar reason, if E's learning technology is better, then shifting down both learning technologies, that has a bigger, sort of proportionally bigger effect on the entrant. And so privacy has this unintended consequence of actually potentially hurting the entrant more than the incumbent, and providing a competitive advantage to the incumbent. That, of course, assumes that privacy is, implemented equally across incumbent and entrant, and obviously that has implications for the way you might want to implement it. And we can show that consumer surplus is also lower in this case when the entrant was previously subsidizing. Okay, so in the interest of time, let me move quickly on to within user learning. So as I said it sort of earlier, within user learning, things are very similar. So basically, we can have the same model, but now we have like consumers infinitely lived. It's the same consumers in every period, and the same learning specification learning function, except now the number of NI is not the data, it's not sort of the number of other consumers in the past, it's now the number of times this consumer has purchased a product in the past. So it's basically for a particular consumer, how often have they used the firm I's product before? That's the relevant data that firm I would have on that particular consumer. And the other difference is we allow the firms to price discriminate based on the consumer's history, which is natural in a framework in which you have customization. And if we do that, then everything can sort of be analyzed from the perspective of an individual consumer. And we can go through the similar kind of analysis, with two-dimensional backwards induction, similar logic. We get exactly the same threshold. So E wins if and only if the difference in standalone values is greater than or equal to the cutoff. The cutoff is defined in exactly the same way as before, and the equilibrium outcome is socially optimal. That's even more obvious now because the consumers are forward-looking, so they're always going to choose whichever firm can create a higher present discounted value of utility from learning. Unlike before, the fact that the firms offer subsidies is no longer the main driver for that result. And Furthermore, it wouldn't hold with myopic consumers. So that's a difference from before. The fact that consumers are forward-looking plays a key role for the social optimality of this result. One difference when we move to within user learning compared to across user learning is it turns out we can show very generally, so with no additional assumptions, that the firms always make more profit, sort of the winning firm makes more profit in equilibrium when there's across user learning compared to when there's within user learning. So within user learning makes the firms more competitive in a sense. And the reason for that is, well, the consumers are forward-looking, or if the consumers are forward-looking, they need to be compensated for not making the losing firm a more competitive option next period. So think about the consumers, they're thinking about which firm to choose. If they choose the losing firm, the firm that's expected to lose, and remember in equilibrium they're sort of indifferent because the winning firm's just offering the surplus to make them indifferent. If they choose the losing firm, then they're going to make the losing firm more competitive option next period. And that's going to benefit them even if they choose the winning firm next period, because it's going to put more constraint on the winning firm's pricing and allow them to get a higher surplus. And so they need to be compensated for not choosing that option. And so the winning firm sort of has to offer them even more. Okay, and so generally, all our comparative static results and implications are very similar, except there's sort of a wider range where data sharing is bad for consumers because now the competitive outcome, the competitive equilibrium is sort of even better under within user learning. One sort of qualification is you need that the consumers are forward-looking for these results. If consumers are myopic, then actually all our results revert back to the across user learning results, and there's no difference between the two settings. Okay, finally, let me say a few words about network effects. I think I have just a few minutes left. So far, network effects haven't played any role. There's sort of two distinct ways in which they could play a role, in which we would get sort of consumer coordination problems, multiple equilibrium, and consumers having to work out which platform or firm the other consumers are coordinating on. So one is if we combine across user learning and learning within the consumption lifetime. So an easy way to do that is to assume that standard pure across user learning model that we went through, but now instead of learning from past users, the firms also learn from the current users. So then obviously when consumers decide which firm to buy from, they have to take into account, they have to think about what are the other consumers going to do in the current period, because that's going to affect how much utility they're going to get in the current period. And of course, if they live multiple periods and they're going to consume over multiple periods, then you can sort of extend that idea to more than just the current period. Okay, and whenever you have these combination, then you're going to get network effects having a real effect on the equilibrium analysis. The other case is when you combine across user learning and within user learning. So in this case, when you have within user learning, then consumers have to think about which firm to choose, because once they start using a firm, that firm's going to get better for them. So it creates this endogenous switching cost. And then, of course, they don't want to be sort of stuck on the firm that's better for them, but no one else is using, because that firm's not going to get better with across user learning. So they sort of need to coordinate, well, which is the firm that everyone else is going to join, and that's the firm I want to join, because I know that it's also going to learn more about me, and it's going to be costly for me to switch to the other firm in the future. So think about Google search. I choose Google search over Bing because it's going to get better for me. It's going to get more customized. It's going to understand my search queries better. And it's also going to get better because most other people are using it. And so even though it's sort of costless, there's no actual cost to switch to Google Bing, from Google to Bing from period to period, because of the endogenous switching costs from within user learning. Essentially, you can get this coordination problem and a real network effect mattering. And once the network effect matters, then beliefs matter. And this is a new source of, or a new reason why you might not get the efficient outcome. For instance, if beliefs favor the incumbent, then consumers will tend to coordinate on the incumbent. Then the entrant will win less often than it should in the efficient outcome. So this is one further factor that affects their sort of welfare result. So I'm out of time, so let me just conclude. Basically, we're saying that data-enabled learning is becoming more and more important and playing a bigger role in competitive dynamics for many products and services. In the paper, we sort of highlight various key determinants of what determines that competitive advantage. One thing we highlight is that there's a difference between across user and within user learning, that equilibrium profits are higher under the former. We talk about when firms' competitive advantage is greater in terms of the learning curve, its position along that learning curve, the remaining learning potential. I didn't have time to sort of focus on the comparative statics, but we do go through those in the paper. And of course, as mentioned at the end, another factor is whether you have sort of real network effects and coordination problem, in which case user expectations are another factor affecting competitive advantage. Okay, so I'll stop here and look forward to the discussion and questions. So let me answer a couple from in the Q&A first. So there's a question about equilibrium efficiency result driven by homogeneous Bertrand nature of competition. Yes, so that's true. I don't think it's sort of a knife edge result. So if you imagined, of course, it's very difficult once you allow for horizontal differentiation to do the model in the way we've done it to solve for the equilibrium and so on. But imagine you could. What we would expect is that as that differentiation got smaller, we would converge to the efficient outcome. If it was, differentiation was there, we'd get some inefficiency, but that inefficiency, I think, is sort of getting smaller and smaller as the products get more homogeneous. We can get inefficiency actually once we move away from our framework. For instance, if we have a finite number of periods instead of infinite period game, then we always have some inefficiency. So, but again, we can sort of characterize that inefficiency, and we can take the limit as the number of periods goes to infinity, and we can show how that inefficiency disappears. So, and also we can sort of characterize what drives that inefficiency, and it has to do with, nonlinearities in the learning curves and things like that. So, yes, I agree, like our special structure gives us a very strong result, but I sort of see it as a bit like a benchmark result. So, of course, we don't believe the outcome's always perfectly efficient, but at least it's a benchmark, and then you have to understand why things might be inefficient in a certain direction or other once you move away from that benchmark. And related to that, I mean, it's not obvious what these inefficiencies are. Like if we go to the finite period model, the inefficiency that you get is very subtle, and it depends on relative curvature of the learning functions, and it's a sort of a very second order effect. So in some way that suggests that efficiency result is important. There's a question with someone who joined late to say, is the learning function, does it have to be linear? No. So the learning function could be any increasing function of any shape. It doesn't even have to be continuous, or certainly not smooth. So is it important that the losing firm stays in the game even if it never has any market share on the equilibrium path? Very good question, and yes, that is important. That is the way that we're able to, like things would be very different if the losing firm exited, obviously, right? Then the winning firm would have monopoly, and that changes the analysis. So we think of it like it's a very handy way that we can get get a tractable model that works well, but it's of course not entirely realistic. So again, think of it like a benchmark. In reality, if there was a little bit of differentiation, then the losing firm would make a little bit of profit and might stay in. We do have some results that we've worked out that are not in the paper where you have sort of stochastic element, like for instance, if the data sharing is stochastic, then there might be a reason for the losing firm to stay in because it has some chance of becoming the winning firm in the future. So we can look at that case. Of course, in reality, the losing firm, this might be just one line of its business. So it might stay in the business because its fixed costs are covered by other lines of business where it is making sales. Whichever justification you prefer, but yeah, we do need that assumption. It does be a very different outcome if that firm didn't stay around. Question on data depreciation. Yes, so if you had data depreciation, you might make the model more like the finite period version. So in that sense, you might also get some on-path inefficiency. Yeah, I entirely agree. I think, there's many variations on this model you could look at, including moving to a finite period version and then introducing other aspects that are difficult to introduce in the infinite period version. And data depreciation would be definitely one of those that would be nice to look at. It's not obvious how it creates inefficiencies, but yeah, well, we already know once we have finite period, we'll have inefficiencies. So it's not easy. It's not clear how you can introduce data depreciation into the framework that we have in a nice, tractable way. But that's certainly an open question. Okay, a question from Joseph. Suppose the entrant is a short run player, how would your equilibrium change in this long run versus short run setting? Right, so you have in mind the entrant is maybe myopic, I guess, or difference in discount factor. So it's forward looking, but it has it's less patient. Not something we've looked at, but it's not a question I've ever been asked. So it's an interesting one. That the entrant. I mean, I would presume that would mean the entrant is less willing to give subsidies, because it's a bit like the learning curve in the future is weighted less. Like the potential increase in value that it can offer in the future is weighted less, and so it would have similar effects to. In what we have in the paper, which is, if they have asymmetric learning functions and the entrant has a lower sort of learning potential, then it's going to subsidize less, and that would give it a competitive advantage to the incumbent. So I would say my guess is it's going to make things better for the incumbent. It's going to allow it to win more often, and it would create an inefficiency as well. So the incumbent would win too often, assuming the entrants just somehow not weighting the future as much as it should from a welfare point of view.
Can you give the explanation of how machine learning already affected the product costing, the current product costing techniques, in order to find optimal pricing for a new developed product?
Yeah, so I saw the question, I read the question, but I don't quite understand what kind of example you mean. So, so all the examples, yes, we have in mind machine learning, improving the product quality.
Okay.
So I'm not sure by product costing techniques what you had in mind.
Yeah. Have you heard about ABC costing technique or
Nope.
traditional costing?
No.
Okay.
That's outside of my area, but do tell me.
Yeah.
Does it
well,
relate to the algorithmic pricing, using AI to choose targeted pricing for customers?
right.
Yeah, so I mean, I don't think pricing is in the scope of what we have in mind with data-enabled learning, because it's something that directly increases the utility from the product. If you're improving the pricing, I think you need a very different framework, right? But it would be it's an interesting, topic to look at, but with a different model.
Oh, okay.
Yeah,
Thanks.
I didn't have any, particular example. I guess the one thing I thought about is, I don't know, it's a little bit different, which is loans. So there's a lot of use of data on individuals to improve the lending decisions. And that can also, of course, affect the pricing. And I guess insurance as well, where the effects are not so much on the product improvement, but on the assessment of which consumers get the loan or get the insurance, and the pricing of that, getting it, improves as you get more and more users.
Yeah, so it's a great pleasure to discuss this paper, a very nice paper. So let me first briefly summarize the main findings and the insight of this paper. So this paper helps us to understand the competitive advantage from data-enabled learning. Start from a very simple virtual competition model between the incumbent and the entrant, asymmetric virtual competition where consumers values as for the standard alone product, SI and SE. So the entrant can come when SE is greater than SI, so very simple, and makes a profit SE minus SI. So what happens if there's data-enabled learning? Data-enabled learning improves the value for the incumbent products to SI plus FI of NI, which is a number of consumer base. Now, this data-enabled learning actually creates a barrier to entry because now the entrant can enter only if SE is greater than SI plus the difference of between the learning capacities, which is related to the consumer base NI and NE. In particular, we can think about, in many cases, the entrant has no consumer base, NE equal to 0, therefore FE and NE equal to 0, or it has inferior data analytics, so FI is greater than FE. So in this case, you can clearly see that the data-enabled learning creates a new barrier to entry. So what happens if SE is smaller than SI plus FI minus FE? In this case, the incumbent will stay as an incumbent. Its profit becomes the difference between these two values. So one important thing here is actually the consumer surplus from learning, FI and I, will be exploited by the incumbent. It will not be passed on fully to the consumers. The second important feature of this model is the competitive advantage will be accumulated across time in a dynamic setting. So if the incumbent wins this period, its consumer value is going to increase to SI plus FI, NI plus 1, because one extra period, there's increasing number of total population 1 for the next period. So if the learning function is unbounded or with very high bound, you can imagine that the incumbent will eventually become non-contestable after a sufficiently long period. So consumer value increases the total number of consumer base, as this model captures a very nice positive feedback loop, which favors the incumbent. It creates a snowball effect. So that actually creates increasing barrier to entry and will discourage entry. So winners takes all in the future. If you win now, you will win in the future, unless the entrant can create a more powerful technology. While competition is intensified when firms can cross-subsidize, because firms are willing to sacrifice its profit now in order to win forever. But if in the case of the entrant, there's a limit or constraint of finance, once again, it will put the entrant on a disadvantageous place. In the paper, it characterized a very nice condition for the entry to come if and only if SE greater than SI plus delta NI and E. where delta Ni and E captures incumbents, capture advantages through data-enabled learning. So I would like to use this model to interpret Google's dominance. As you all know, Google's case becomes very hot after DOJ's lawsuit. And also it's a very famous Google Fitbit merger case under investigation in many jurisdictions, including the European Commission and ACCC. So if the merger is approved, Google can leverage its dominance into the market of wearables. Imagine that when Google acquired the Fitbit watch, it can integrate Fitbit into its ecosystem. So now consumers can derive extra value, FI, from using the same platform. They can store the data on the Google Cloud and integrate with other Google products like Google Nest. So the added value increases with Google's consumer base. So according to this model, you can see a very, very significant effect as the entry barrier. The question now we can ask is, under such kind of merger, can a small rival, like manufacturer of smartwatch, wearables, survive in that market? It can survive only if this condition is satisfied. So let's assume the entrant and the incumbent, they have the same learning capacity, F equal to theta x, let's say linear, but the consumer base NE is negligible compared with Google. Google has about 1 billion consumer base. Then you can see that delta Ni 0 equal to theta Ni. A very simple calculation, you can see intuitively, this entry barrier is huge. So you can imagine that after merger, small wearable manufacturers have no chance to survive. And Google will monopolize the whole market, given time, maybe 2 or 3 years. So using this simple model, we can see actually Google's expansion through acquisition becomes a serious threat to competition because of its huge capacity of data-enabled learning. Finally, I would like to give several comments on the paper. First of all, I like this paper very much. It's a very nice paper with significant contributions to the literature and competition policy. The paper employs a very simple and neat repeated game setting and captures the key feature of data-enabled learning, a positive feedback loop. So there are two key modeling features. One is an increasing learning function, Fi or Fe, and then repeated Bertrand competition. Regarding on the learning function, the learning function here is summarized. The learning effect here, is summarized by in a learning function Fi. I feel it will be helpful to provide further discussion on its micro foundation. For instance, as Julie mentioned, the within user learning function is related to consumer switching cost. So here switching cost actually will can be endogenous or will increase when you use this product more times. So its micro foundation here is relatively easy to illustrate. I think it will be very useful to have a subsection interpret this micro foundation. While cross-user learning micro foundation may be relatively difficult, but once again, I think it will be useful to provide this. So regarding on Bertrand competition, so winner takes all simplifies analysis, but the pricing effect is missing here. So when products are differentiated, incumbent may not be able to take all consumers because there's a pricing effect. But still, I think it may engage in below cost pricing in order to serve more consumers in the current period, and then it can exploit consumers the added value from learning from the next period. I believe the main insights will preserve in a general setting with product differentiation, but of course I understand it's very difficult to solve the equilibrium in this repeated again setting because of dynamic pricing effect. Finally, I think the model can be used to interpret Google's dominance from its superior learning technology. In particular, it's a very hot case of Google Fitbit merger. So in this sense, I think it will be useful to discuss this case in the paper, maybe provide some section or subsection. And I believe you can provide very important policy implications. In particular, data sharing is considered as an important remedy by the European Commission for this merger. But it is not clear what the impact of data sharing. Well, in your paper, you can discuss it in a very easy way. And also, I think it needed to, in the discussion, needed to take into account the asymmetric learning functions between Google and the small competitors. Google data analytics and AR technology is uncomparable by the others. Okay, thank you very much. That's my comment.
Thank you, Zhijing, for the discussion.
Okay.
So Julian, there are still two questions regarding, I think, data ownership in the Q&A. Do you want to answer the question?
Okay, sure, I'll have a look. Yeah, thanks for those comments as well. And we can discuss offline, I guess, some of those things. But for the Q&A, suppose consumers can carry out a switch their data from to the company. Could you model extend to analyze this case? So I think what you have in mind is something like data porting, that I can choose to allow my data to be used by the rival. That is definitely something the model could be extended to look at. In a way, it's very similar to data sharing. The difference being that with data porting, the consumer endogenously decides when to share the data, whereas in data sharing, it's the regulatory environment that decides when to share the data. So because the consumer decides, it can be used in a more strategic way by the consumer. And so the implications for consumer surplus and so on could be different. That's something we haven't done, but it's definitely on our list of things we could do with this framework. Melody asked, if instead of buying data from a third party, a separate market opens up with a measure of NA new consumers and firms can choose a different price in this new market, will equilibrium be socially efficient in this case? Yeah, so I don't see why not, because that would be just the same as basically saying, we're just going to increase the market size, right? Like at some point, instead of one new consumer this period, this instead of measure one new consumer this period, we're going to measure NA consumers this period, where NA is bigger than 1. And I don't think anything particularly depends on it being measure 1, right? Other than tractability. So yeah, intuitively, I think that equilibrium, social efficiency should be preserved. The key difference when buying from a third party is you're not making that decision based on, acquiring the data based on attracting the consumer. You're making that decision based on acquiring the data based on being willing to pay more to the third party. So that creates the inefficiency.
Okay, I think we need to close now. Let's thank Julian again for his presentation, and also Zhijing for his discussion.
Thank you. Yeah, thanks
Thank
for
you.
Thanks, Julian.
the
Thank
nice
you.
comments and questions.
So we will continue to have more seminars in this seminar series. So please, maybe you can follow our schedules on our website. Okay. So see you, everyone.